Hello everyone, today we'll be talking about the principle of least action or the stationary action principle, which I will discuss shortly, leads naturally to the Euler-Lagrange equation, with certain assumptions of course. But let's first talk about how we should reformulate Newton's equations to work for generalized coordinates, meaning that for say n particles around a space, certain amount of particles, and how we should formulate Newton's second law to work for these dimensional spaces. So first we know that work done is defined as a line integral from f dot ds, and then we know that work done is a conservative vector field. So essentially around a closed curve, this is evaluates to 0. So by the fundamental theorem of line integrals, you can express your vector field as the gradient of some potential function, which is what we define now as potential energy. So for some arc length parameter, we write partial v and partial s. So this is just a matter of redefining what Newton's second law tells us. And then we know that force is the rate of change of momentum. So we just write p dot, let's just put a subscript s minus partial v on partial s. So that's how we redefine our Newton's second law of motion as the gradient of a scalar potential function. And then so with this we need to generalize this even further by introducing n particles, say n particles with a certain amount of coordinates in a 3n dimensional space. Because recall that a particle traversing through some configuration space, this is a configuration space, requires at least two translational and one rotational, and then degrees of freedom, and then so you amount to 3n degrees of freedom here. So suppose we just write PA equals to m a x dot a. So where we write all the coordinates of the n particles as xa. So this is just a shorthand notation for the coordinate vectors of all the particles, the way you do in linear algebra as well. So once you do that, you have ma x dot a. It's going to be equal to minus partial v on partial x a. So that's your reformulated Newton's law, second law, for a 3n dimensional space with 3n degrees of freedom. Now we're going to define the Lagrangian, which I'm sure you're aware of, is of xa. So this works for any n particles in 3n dimensional space. Notice that under this assumption is that if you have holonomic constraints, which means some equation which has variables above 3n degrees of freedom, with holonomic constraints you can reduce them down to a set of constraint equations. But with non-holonomic constraints you can't do this, and you fail at the assumption that there is a 3n dimensional space. So the Lagrangian here only works for holonomic constraints. So now you have let's define the Lagrangian as the kinetic energy term minus the potential energy term, and we'll see why all these work later on. So we define what an action is first. Around a closed continuous curve, we call what we define paths. So this is one possible path around 2 points, and these are closed compact sets. So there is only one path taken by the system, and this path actually is the extremum of the action. So first we define the action, xa of t. That's going to be equal, so at time I, so we write the position here as I, xi, xf, and then at time I, the initial time and the final time. So we evaluate the Lagrangian like this, and this is how we define our action. So we're gonna show how by taking the extremum, which could be a minimum, a maximum, saddle point, leads naturally to the Euler-Lagrange equation. So as you can see, there is actually a few assumptions there. So let's see how it works. Consider a proof. So the path taken will be the extremum on S. So we try to vary the path slightly by introducing sort of an infinitesimal term like this. So delta is around 0, but small, a very small term, and we must fix the endpoints of the path. So that's going to be like this. We fix the endpoints. So the endpoints are not changing, which would cause quite big problems. So notice in this idea is that your path is a closed continuous curve. So in a matter of the next lines, we'll use certain principles and explain mathematically why they're possible. So we talk about the change of action, as we define appropriately here, is the change in the Lagrangian, the integral here. Then, so this is fine. And then we can bring it in. Recall that you are working in a closed compact set. So the set is you're evaluating over Ti and Tf over a closed continuous curve. Your differential operator and your integral operator can be swapped. So that's fine. And then if you can consult any real analysis textbooks, and they should say that. So here you can use the multivariable chain rule, or you could use the total derivative in a sense. Depends on what you call it. So that's partial L, partial XA, delta XA, plus partial L, partial X dot A, and delta X dot A. Remember that the Lagrangian was dependent on this, so that makes sense. So that your total derivative, that makes sense. And then what you write next, you integrate the second term by integration by parts. So this is a little tricky to choose which ones you want. So it helps to know what the Euler-Lagrange equation actually is. So it's actually just partial L, partial X dot minus partial L, partial X. So we are trying to arrive at this, or at least prove that it works. So here you're going to want to pick, since here it tells you the time derivative of this term, you're going to want to pick this as the U, so that's partial X dot A, and then dV, that's delta X dot A. So your du is going to be d on dt, partial x dot A, and then v is going to be delta x A. So perfect. So now you have TF, TI, partial L, partial X dot A, XA, delta XA. So your integral for this guy is going to be partial L, partial X dot A. So UV, delta XA. So let's get this out, dt minus the integral TF, TI. So we're going to integrate TF, TI, and then V du, so delta XA, d on dt, partial L, partial X dot A, dt. Now these parts are separate, so and this integral is the same. So we can bring it back. So that's TF, TI, partial L, partial XA, delta XA, minus delta XA, d on dt, partial L, partial X dot A, dt. And then outside here you have, outside the integral you have partial X dot A, delta X evaluated on df and di. Now initially, in our initial condition we said that the endpoints should not change and should be 0. So essentially we're evaluating 2 points of 0. So this actually turns to 0. So if you have substituted in delta TF, delta TI, that's going to be 0. So this term turns to 0 because the endpoints don't change. And then you're left with this integral. Now doing some simplifications, you will see that this should work. So A minus d on dt, partial L, partial X dot A. So the requirement that the action is an extremum is if your delta S, that's equals to 0. And we see that if the extremum is 0, then what we get is that partial L over partial X dot, partial L over partial XA minus d on dt, partial L over partial X dot A, that equals to 0. And then this is known as the Euler-Lagrange equations. So we have successfully derived this Euler-Lagrange equation. So to finish the proof, we need to show that these Lagrange equations are equivalent to the Newton's formulation. So we see that partial L over partial X dot A, that's equals to the momentum, the canonical momentum here. So this is the force. And then you have partial L over partial X dot A, that's equals to minus partial V over partial XA. So this is equivalent. So what this tells you is that the Newton's equations, the Lagrange equations, are equivalent, and that when you take the extremum of the action, it naturally leads to the Euler-Lagrange equation, of course, provided you have some assumptions, many assumptions actually, and that's it.